Yeah, thank you very much, and yeah, it's a pleasure to speak in this meeting. I really would have loved to be there in person, but unfortunately I have to be joining you remotely. And yes, so the original title of the talk was quite long, but then someone suggested to me that this more catchy phrase, "freedom for free," kind of captures what is the main point of it. Okay, so what am I going to be talking about? Well, the main topic of the talk is some kind of interplay between problems that arise in dynamical systems and study of group actions, specifically actions of countable groups on Polish spaces, and some sort of questions or tools and techniques from combinatorics. And this interaction is affected by means of using tools from descriptive set theory, and in particular from this field called Borel Combinatorics, which studies, roughly speaking, what sort of combinatorial constructions can be performed within the sigma algebra of Borel subsets of a Polish space. Yeah, so let's jump right in. Here are the main characters in this story. Throughout the talk, gamma is going to be a countable group, infinite countable group. And whenever I talk whenever I have capital X anywhere on the slide, this is going to be a Polish space on which the group gamma is acting by Borel automorphisms. So a principal example of such an action for me is going to be the shift action, which is defined as follows. So first of all, lowercase q is going to be a natural number, also always throughout the talk. And because this is a set theory workshop, I'm going to identify q as the set of natural numbers that is strictly smaller than q, so 0, 1 up to q minus 1. And q to the gamma is the space of all functions from gamma to q, which I refer to as colorings of gamma with q colors. So I think of the elements of q as colors, and I refer to such mappings as colorings. And this is a topological space where q has the discrete topology, and I put the product topology in q to the gamma. So really, this is a copy of the Cantor space. And the shift action of gamma on this group is on this space is given by this formula, which just says that every group element gamma acts on a coloring x by just permuting the coordinates. So formally, if x is an element of q to the gamma, then gamma times x is also an element of q to the gamma, which when evaluated in the group element delta, that's how it's computed, x of delta times gamma. Right, so we use gamma to shift all the coordinates. That's what's called the shift action. Okay, so this is kind of, at least in dynamical systems, this is one of the most important examples of group actions. The nice thing about it is that for any countable group, I can construct this action without knowing anything about the structure of the group itself. And I can also consider subsets in this space. So a subshift is a closed shift invariant subset of q to the gamma. Okay, and so I can restrict the action, because it's shift invariant, I can restrict the action to the subshift. So I can study what sort of dynamical properties subshifts can have. This is a big avenue of research in the study of group actions. Okay, one more piece of terminology I will need is I will say an action is free if every non-identity group element moves every point. So for every point x, and for every group element gamma that's not identity, gamma times x is not equal to x. In other words, the stabilizer of every point x is a trivial subgroup. And if my action is not free, I can always find inside of it the largest invariant subspace in which the action is free. This is called the free part of the action. So this is my notation for it. The free part of x is going to be the set of all points, little x, such that gamma times x is not equal to x for every non-identity group element gamma. Yeah, so for example, the shift action itself, this action of gamma on q to the gamma, is not free. For instance, because the constant function, any constant function, actually is fixed by every group element. No matter how you shift it, it remains the same. But if q is at least 2, then this free part is non-empty, and in fact it's a co-meager in the postgre. But typically it's not going to be closed. That's another important thing to know. Okay, so these are some basic notations. Now, as I said earlier, what we're going to try to do is understand some kind of interaction between these dynamical questions about the actions and their combinatorial counterparts. And there is sort of a well-known duality between some types of dynamical and combinatorial questions of this sort that is affected by this one-to-one correspondence. So if I have my space X on which the group gamma is acting, I can look at the colorings of X with Q colors, and this somehow, I think of these as combinatorial objects, just assigning colors to the point. But any such coloring gives rise to an equivariant map from X to this shift space Q to the gamma. And the way this works is, given the coloring F, I define the coding map, which I'm going to denote pi sub F. This is a map from X to Q to the gamma. And how is it defined? Well, pi sub F of X, this is going to be some kind of coloring of gamma. And the color of a given group element, little gamma, is just what you do is you take X, you move it by gamma, and you see what the color of that point is under F. So this is the definition. So you get F of gamma times X. And you can check, it's kind of easy to see from the definition of the shift action, essentially, that this map is going to be equivariant. And conversely, if you have an equivariant map from X to Q to the gamma, then it actually corresponds to a unique coloring F. So it's a coding map of a particular coloring. So this is really a one-to-one correspondence that is well understood. But this means that I can, on the one hand, ask questions, sort of dynamical questions about these equivariant maps, or I can ask combinatorial questions about the colorings. And what we're going to try to understand is the interplay between the two. So what sort of dynamical questions can we be asking? So I'm going to phrase it in terms of the colorings. I'm going to say that the coloring of X, this F, is aperiodic if the image of the coding map is contained in the free part of the shift. So in other words, if I take any point in X, I apply this equivariant map, I get a point in Q to the gamma. Well, this point has to be moved by every group element, by every non-identity group element. In other words, somehow, if you think about how coding maps work, it sort of means that if I take a point in X and I move it by some non-trivial group element to some other point in X in its orbit, the coloring of the orbit looks sort of different from those two perspectives. And I can even introduce a stronger condition. I'm going to say that the coloring is hyper-aperiodic if not just the image of the coding map is in the free part, but even the topological closure of the image is in the free part of the okay, so these are definitions, and the basic question is, do such things exist? So the answer is yes, essentially always. This is a really nice and powerful theorem of Seward and Tucker-Drob, which says that if you give me any free Borel action of gamma on the Polish space, I can always find a Borel hyper-aperiodic coloring with just two colors. Yeah. So this is a really strong result. In particular, various weaker statements are already highly non-trivial and require complicated proofs. So, for example, so here I said hyper-aperiodic, so which is the closure of the image of the coding map is in the free part of the shift space. But even without this closure statement, just making an aperiodic coloring already it's already a very non-trivial problem. So in other words, right, what this says is that for every free Borel action of gamma on the Polish space, you can find a Borel equivariant map to the free part of 2 to the gamma. And yeah, this is already non-trivial. And this theorem is the only way how we know how to prove this somehow. It just so happens that even if you want to construct an aperiodic coloring, it just whatever techniques we know how to use automatically make it hyper-aperiodic as well. On the other hand, you can maybe ignore this whole equivariant map business, because if I have a hyper-aperiodic coloring like this, if I look at the closure of the image, this is a shift invariant and closed subset, in other words, a subshift, contained in the free part of the shift space. So it follows from this theorem that there exists a non-empty subshift contained in the free part of 2 to the gamma. And this also is already highly non-trivial. And this is the earlier theorem of Gao, Jackson, and Seward that such a thing exists. And the construction is quite intricate. Okay, so these are the sorts of dynamical questions we can look at. Now, what about the combinatorial side of the story? What are the combinatorial questions we're asking? So here's a slide with a big definition, and maybe on the next slide I'll try to explain why I think of this as capturing combinatorial type of constraint you can put in the coloring. So the notion that we're going to use to sort of identify what we mean by combinatorics here is the notion of a subshift of finite type. It's a subshift of a special properties. So here's how this is defined. We fix the following information: some kind of finite subset of the group. Let me do this W, and I'm going to call it a window. And also some kind of set, say capital phi, of maps from W to Q. In other words, colorings of W with Q colors. And then I can form the following set S, which is going to be the set of all points in Q to the gamma, with the property that if I take this point X, I'm shifted by any group element gamma, and then I look at the restriction. So this gamma times X is now a coloring of gamma. I look at the restriction on the window W, and then I check whether or not this belongs to my special subset phi. And if the answer is yes for every group element gamma, then I put X in S. It's kind of easy to see from the definition that this is a subshift, and subshifts of this form are called subshifts of finite type, or SFTs for short. So this is my attempt at an illustration. If the group is, say, the integers, which is a group I can draw, and maybe my window W is these 3 consecutive elements, then what's happening is, okay, I've given this point X, which is just a coloring of the group. What I'm allowed to do, I'm allowed to just see the part of this coloring that's within this window, and then by looking at this, I can check whether or not it's in my special set phi. And then I can slide the window around and put it in every possible location in the group. And for each of those, I check whether or not the coloring is in phi. And if the answer is yes everywhere, then I satisfy the condition, and now I'm in the subshift. And somehow you can think of this as a combinatorial constraint because it's kind of like a local restriction on what the coloring can look like. Locally, it has to look like one of the colorings in the special set. And these are sorts of problems that people in combinatorics may study. Yeah, and one more piece of terminology. Now, if I have a coloring of my polar space X on which gamma is acting, I'm going to call it an S coloring, where S is a subshift of finite type, if the image of the coding map is an S. So let's say an example, which maybe justifies me saying that this is a combinatorial notion. In combinatorics, people study graphs rather than groups, mostly. Or, well, at least this is one of the objects people can study, the graph. But given a group, I can always can kind of naturally associate a graph to it in the following way. Let me fix a finite subset of the group, let's call it F, that doesn't contain the identity element and is symmetric, meaning that if it contains some element, it also contains its inverse. Then I can define the Cayley graph of gamma corresponding to the set F, which is a graph whose vertex set is gamma, and for every vertex gamma and an element sigma of F, I put an H from gamma to sigma times gamma. That's the definition of a graph. And I can do the same definition for an action. If gamma is acting on X, I can define what's called the Schreier graph of this action. It's the same definition, except that instead of gamma, I'm using as a vertex set, I'm using X. So the vertex set is X, and for every point in X and every element sigma in F, I put an H from X to sigma times X. It's the same definition. And in particular, if the action of gamma on X is free, then the Schreier graph was obtained just by placing a copy of the Cayley graph on each orbit of the action. That's what's happening. Okay, so we have these graphs. In graph theory, one of the main things you do with graphs is try to color them properly, where a proper Q coloring of a graph is just the coloring of the vertices with Q colors, such that the colors of adjacent vertices are different always. Okay. And usually the question is, what's the smallest number of colors you need to construct such a color? Okay, so this is clearly a very combinatorial notion. But now if I look at the Cayley graph of gamma, and I look at all the proper Q colorings of this Cayley graph, so this set of solutions to this combinatorial problem, this is a subshift of finite type. I'm going to call it, boldface COL of FQ. This is the set of all proper Q colorings of the Cayley graph of gamma corresponding to the set F, and this is a subshift of finite type. It's kind of maybe it should hopefully be kind of clear why. The window, I mean, how do you check whether a coloring is proper of the Cayley graph is proper or not, right? Well, you need to look at each point, and you need to look at whether or not its color is different from the colors of its neighbors, which are obtained by just moving this point gamma, say, to sigma gamma, where sigma runs over F. So the window is something like F together with the identity element, and you move it around in the group, and you check in each of those subsets that the color of the middle point is different from the colors of all the neighbors. And if the answer is yes, then it's a proper color. So this happens to be a subshift of finite type. And similarly, okay, whatever other combinatorial problems you want to solve, like you want to find a perfect matching in the Cayley graph, this can be encoded as a subshift of finite type as well. Things of this form. So combinatorial questions kind of naturally can be encoded by subshifts of finite type. And moreover, remember this definition, this notion of an S coloring given a subshift of finite type. I say that an S coloring of an action is a coloring such that the image of the coding map is contained in S. Well, a COL FQ coloring of a space X is exactly the same thing as a proper Q coloring of the Schreier. Okay. So these general notions generally kind of just extend this from this particular subshift to any kind of subshift. Okay, so now these are sort of combinatorial questions you can now ask. What do we know about them? Well, here's a representative example of a theorem that's known. This is essentially due to Kekker, Selesky, and Todorcevich. It is not quite stated this way there, but you can easily use the same proof to get this result as well. If I have a free Borel action of gamma on some Polish space X, let me take some finite set F as before, and let's say D is the cardinality of F. So notice that by construction, every vertex in the Schreier graph has exactly D neighbors, which somehow should suggest that D plus 1 colors should be enough to color it. If you have a finite graph where every vertex has D neighbors, if you color the vertices one by one, and you have D plus 1 different colors, that always is going to be enough. Well, it turns out that in this setting, it's enough. D plus 1 colors suffice for a Borel coloring. So there exists a Borel proper D plus 1 coloring of the Schreier graph. And actually, so here I'm saying Borel, you can even strengthen this to make it continuous under some reasonable assumptions. So if the action is continuous and if the underlying space is zero-dimensional, meaning that the topology is generated by closed sets, then you can make this function f continuous. It sort of makes sense to assume that the space is zero-dimensional because f is a function from x to a discrete space. So pre-image of every point has to be closed. So we had better have enough closed sets to cope to such function exists. And thankfully, this isn't too restrictive of a condition. A lot of natural spaces that we study are zero-dimensional, like Q to the gamma is zero-dimensional, or even if you start with something like R, you can make it zero-dimensional by removing just, in this case, countably many points. R minus Q is, this is the bare space, it's zero-dimensional. Any subspace of a zero-dimensional space is zero-dimensional, so any subshift is going to be zero-dimensional. And also, in general, the second claim implies the first one, even though in the first one we're not assuming anything about the topology on X except that it's Polish. And this is because, given a Polish space, you can change the topology without altering the Borel set in such a way that the topology becomes zero-dimensional. All right. So, okay, so we know that there exists a coloring with D plus 1 colors in that setting. So again, this is the same situation as before. We have a free Borel action of gamma Polish space X. We have the set F of size D. And we already know that there exists a Borel D plus 1 coloring of the Schreier graph. But now, can we combine and we also know that there exists a hyper-aperiodic coloring. But can we combine these two together? Can we find an aperiodic or even hyper-aperiodic coloring of the Schreier graph? And okay, so it turns out that the answer is yes, but even much more is true. So this is just the consequence of a general theorem about, instead of looking specifically at proper colorings, we study aperiodic or hyper-aperiodic S colorings for subshifts of finite type S. So let S be a subshift. So what's the general setting? Let S be a subshift of finite type. And so we already have to have, if we want an aperiodic S coloring, there has to be an S coloring to begin with. So let's assume that we have already constructed a continuous S coloring of the free part of the shift for some effect. By the way, this assumption is equivalent to saying that every free continuous action on a zero-dimensional Polish space admits a continuous S coloring. So somehow we don't lose any generality by just looking at the free part of the shift space here, because actually this is the same as to say this for all such actions, for all free continuous actions. This is a result of myself and Brendan Seward independently. Okay, so assuming that such a thing exists, what we want is to find an aperiodic or even hyper-aperiodic S-color. Yeah. So again, this is the setup. We have a subshift of finite type. We already have this F, which is a continuous S-coloring. And let me say just pi is the coding map of F. So it's a continuous equivariant map from the free part of the shift to S. So when we want to construct an aperiodic or hyper-aperiodic S-coloring, well, the problem is that this information may not be enough to conclude that such a thing exists. Ideally, we would just say, okay, there exists an aperiodic one then. This is this freedom for free. I want to make it aperiodic just without having any extra assumptions. Well, that is not going to work. And the basic problem that can occur, the easiest to imagine, is that what if this SFTS contains a fixed point? So a constant coloring, in other words. Then the constant function, the corresponding constant function, is continuous, and it's an S coloring. But of course, the fact that this constant function exists gives no reason to expect that there also exists an aperiodic coloring, right? S could be just a single point, in fact, just this fixed point and nothing else. So that's a problem. There is a more subtle problem that can occur, which is that, okay, maybe there isn't just a fixed point of the action, but maybe still there is this particular group element gamma that fixes every point in the image of the coding of pi. And then there is no hope, there's no reason to expect that we should be able to get rid of this and get some colorings which are not fixed by this group element. Okay, so the main result is that actually this is the only thing that can go wrong. So in this setting, if you can check that there isn't a group element, non-identity group element that fixes every point in the image of pi, then in fact every free Borel action on the polar space admits a Borel hyper-aperiodic S coloring. So as long as you check this very weak assumption, you get the hyper-aperiodic colorings for free. Okay. So for instance, this is a strengthening of the Seward and Tucker-Drob theorem. The way you do this is just you take S to be just 2 to the gamma. Okay, so there are no restrictions, just the whole shift space. And look at the free part of 2 to the gamma. Well, the inclusion map is continuous and equivariant. So this is our map pi. And now every free Borel action in a polar space, but okay, this is free, right? So there's no group element that fixes any point in the image. And therefore, every free Borel action in a polar space admits a Borel hyper-aperiodic coloring. That's the conclusion, which is the Seward and Tucker-Drob theorem. Okay, but okay, but also as I promised, as a corollary, we get that every free Borel action on the polar space admits a hyperperiodic proper D+1 coloring of the Schreier graph. And let me very quickly let me see how much time. I don't have that much time, I think. So maybe I'll just kind of wave my hands in the direction of the argument. The main point here that I'm trying to make is that what we're trying to get is this hyper-aperiodic coloring. So we want to get the coloring such that, you know, if you look at the corresponding coding map, in the image, every point has trivial stabilizer. No group element, no non-identity group element fixes any point in the image. And in fact, even in the closure of the image, right? But by this theorem, the only thing we need to be able to do is to construct an equivariant map, a continuous equivariant map, where this pi, where no group element fixes every point. So for each group element, if I can find one point that's not fixed by it, then I'm done. So what we need to do now is we need to find a continuous proper coloring of the free part of some shift, and I'm going to take here 3 to the gamma for convenience. Somehow that turns out to be useful. So of the Schreier graph of this action, which I'm going to call G, such that no non-identity group element fixes every point in the image. And this is somehow much easier than making sure that it doesn't fix every point in the image. Yeah, and okay, so there's some explicit construction, which maybe in the interest of time I won't go through. Okay, the point is that somehow you can sort of fit it into just a couple slides. If you write everything out, it's less than half a page. And the way this works is let me emphasize this last step. You know, okay, in the last part, so you construct a specific coloring, and then they just say, oh, let's take a non-identity group element gamma, then we need to find some point such that f of x is not equal to f of gamma x. That's what we're trying to do. And okay, and depending on gamma, you construct an element. So the element somehow constructed with respect to gamma, and that's why it's easy to do. But the conclusion is that you can make the mapping actually hyper-aperiodic. Yeah. So let me instead of going into detail about that, let me say a few words about further consequences of this. So here I needed to still do something, I need to construct stuff, but actually there are many cases in which literally no extra work is required. So let me, given that, again, it's the same setting as before, pi is this continuous equivariant map, and let's call the stabilizer of pi is just the group elements that fix every point in the image of pi. Ideally, we want this to be just trivial, just the identity group element and nothing else. Well, it's not too difficult to show that using the continuity of f, that unless f is just a constant coloring, the stub pi is a finite normal subgroup of gamma. So the fact that it's a normal subgroup is almost immediate from the definition, but the continuity of f also allows you to show that it's finite always. And what this means is that if gamma doesn't have any non-trivial finite normal subgroups, then this group must be trivial, right? So if gamma has no non-trivial finite normal subgroups, and if our coloring f is not a constant coloring, then we automatically get the conclusion that every free Borel action of gamma on a polar space admits a Borel hyper-aperiodic S coloring. So this really, we're kind of getting this result completely for free. And you know, in many cases, f just cannot be constant at all. So here's an example. Let's consider the group z to the n. And let f be the standard generating set, symmetric generating set of size 2n, the basis vectors and their inverses. So Gao and Jackson constructed a continuous proper 4 coloring of the Schreier graph of the free part of the shift of z to the n. Okay, let's take this as a black box and observe that z to the n has no non-trivial finite subgroups, right? And obviously this proper coloring is not going to be constant because adjacent vertices have different colors. Therefore, every free, for free, we get that every free Borel action admits a Borel hyper-aperiodic proper 4 coloring of the Schreier. Right, where the previous result that I mentioned, I guess there are 2n generators, so it gives us 2n plus 1 coloring, but actually 4 colors are enough. Which is, and this is just immediate from the Gao-Jackson result. We don't need to know anything about how this continuous coloring is constructed. But actually, I should say that it turns out that you can get the same conclusion for 3 colorings, which is interesting because there doesn't exist a continuous proper 3 coloring of the Schreier graph, and yet somehow it's possible to construct a Borel hyper-aperiodic proper 3 coloring always. So yeah, you should observe. Maybe I should have emphasized there is a little bit of a trade-off because the assumptions that we're using is that the coloring that we establish is continuous, and that's really important for the proof. And this hyper-aperiodic coloring we get is Borel. So we lose continuity and replace it with Borel, but we get this extra condition of being hyper-aperiodic. And this approach doesn't work for 3 columns. So it's kind of interesting to understand what's going on here. It's a little bit mysterious, I think. Okay, so actually you can do even more. Even if this subgroup stub pi, this finite subgroup, is not trivial, you can essentially make the coloring as close to aperiodic as is reasonable in this setting. So you can always find a subshift S prime inside of S such that every point has stabilizer exactly equal to this stub pi, this like smallest group of elements that we couldn't get rid of, and every free Borel action in the polar space admits a Borel equivariant. So if this is trivial, then S prime is aperiodic, and we get the result. So just in the last minute, I guess, let me very briefly wave in the general direction of what the proof is. And the proof is very combinatorial. Somehow this feature of these Borel combinatorics or descriptive set theoretic combinatorics or dynamics or whatever you want to call it, is that really the arguments are very, very combinatorial, and a lot of the time intuition from just classical finite graph theory or something like this is what allows the proofs to go through. So okay, so the proof is split into 2 parts. These 2 lemmas. So the first one is, okay, this is the setup that we're in. We have a subshift of finite type. We have a continuous S coloring of the free part of some, k to the gamma, and pi is the corresponding coding map. And let me just assume that the stabilizer group is trivial for simplicity, so they don't have to worry about it. then what we can find is some Cayley graph of gamma. So we can find a finite set F of some size D and some integer L that's at least D plus 1, maybe greater. And what's important, we get a continuous S coloring of this space. Well, this is, remember, this is the space of proper L colorings of the Cayley graph of gamma. So this is the subshift. This is the space of colorings. So we can find a continuous coloring of this space such that the stabilizer of the corresponding coding map is still trivial. And this, so somehow, weirdly enough, in the proof, these colorings, these proper colorings come up. So this is where kind of combinatorics makes its way in. And the main advantage of this is that what really is going on here is that we started with a continuous coloring of the free part of k to the gamma, and as a result, we produced a continuous coloring of this space. And the reason why this is good for us is because the space is compact. This space isn't compact, but this is. So now we have a continuous function in a compact space that's much nicer to work with. And then there is the second lemma, which says that now assume the conclusion of the first lemma. So we have this continuous coloring of this compact space. Then, now if you give me any free Borel action in a polar space, what I can do is I can properly color the Schreier graph of this action with L colors, so that this composition is hyper-aperiodic. So maybe this is the picture to have in mind. There is X, C is a coloring of X, so there is the equivariant corresponding coding map pi C, and because it's a proper coloring of the Schreier graph, it lands in the space of proper colorings of the Cayley graph, so here. And now we have this coloring G of this thing, and so this composition is going to be the hyper-aperiodic map that we okay, it's a kind of concatenation of these two gives us the result that we want to obtain. And how do we prove these things? We use a very combinatorial tool called the continuous lowest local lemma. So the lowest local lemma is a device in probabilistic combinatorics dating back to Erdős and Lomas from the 70s. And roughly, it says that if you want to find a coloring that satisfies some local constraints, for instance, an S coloring for some subshift of finite type, then if you calculate some things, you bound some probabilities, you compute some numbers, you plug them into a formula. If the formula, some inequality, if the inequality is satisfied, then a coloring exists. And this is as much as I'm going to tell you about the precise statement. But I should add that this is not the only application of the local lemma. There have been many applications in dynamics or descriptive combinatorics recently. And if you want to know more, you can go to this link and see a 3-hour mini course that I gave on the applications of local lemma in this setting. So I will not say much more. But in this situation, we need this coloring to be continuous. So there is this continuous local lemma, which essentially is the statement of similar form, but you need much stronger numerical assumption in the beginning. So there is some work required to make it hold. Okay, and so just to finish, some open questions. As I said, we're tracing continuity for somehow Borelness and hyper-aperiodicity. Well, what if we only have a Borel as coloring to begin with? So can we prove some similar result in this situation? And I don't know. And I don't know even what the statement would be. So this subgroup, the stabilizer group, kind of doesn't tell you anything anymore, because in the Borel setting you can change F on one orbit, make the image of one orbit aperiodic, and now this group is trivial, but it doesn't help you. And here maybe a specific question that you can ask that's kind of in the spirit, which is, suppose we already have a Borel aperiodic S coloring of the free part of the shift. Does it follow that there also exists a hyper-aperiodic one? I don't know any counterexamples to this. All the constructions that we have for building aperiodic colorings just automatically, as a byproduct, make them hyper-aperiodic. So is this implication always true? I don't know. I think this is an interesting question. And that's all. Thank you.